Good morning. Today, I'd like to talk about the third of the classical tests of general relativity, that is, gravitational redshift. At the moment, we'll continue to use the Schwarzchild metric. In a way that's similar to that in special relativity, if I wanted to move an object around a path in the Schwarzchild field, and then wanted to know the invariant proper time interval, then I could calculate it using the space-time interval. We have to think of doing an integral because the components of the metric change as we go from point to point of space-time. On the other hand, if I had a stationary object, I could calculate its proper time interval by using only the metric evaluated at the location of the object, and that's the point of view that we're going to take here. Assuming that we stay in the region where g00 is negative, the absolute value of it will just be 1 minus 2gm over r. The proper time between two events will then be given by this formula. And since all coordinates except the time coordinate is constant, I can simplify it to this form, keeping in mind that in this context, the r is actually constant. We'll imagine that we have an individual named Tom located at r coordinate, r sub Tom, which is outside the region where things are going to get a little strange. We'll have to talk about that later. Imagine that we look at this situation at a certain coordinate time t, and we allow an amount of coordinate time delta t to pass. The amount of proper time that Tom will measure in that situation is given by this formula. At first glance, this doesn't seem to be much use because space-time doesn't come with delta t equals so-and-so marks drawn on it. It turns out that we can actually get something useful out of this information, though. I can imagine having another stationary individual named Jem. Just as with Tom, if an amount of coordinate time, delta t, passes, the corresponding amount of proper time, as measured by Jem, will be given by the same sort of a formula. This is going to allow me to compare Tom's proper time with Jem's proper time. By looking at the ratio of the two proper times, a miracle happens. The coordinate time, which is difficult to measure in any case, disappears from the equation, and this gives me the ratio of the amount of proper time according to Tom as compared to that as measured by Jem. It's important to understand that delta tau Tom over delta tau Jem could conceivably be measuring the time between vibrations in an electromagnetic wave. It could measure aging, it could measure radioactive decay. So this really is going to compare time for Tom versus time for Jem. I want to look at two special cases now. The first case is where Jem is so far away from the gravitational source that the square root on the bottom is basically 1. If the radial coordinate of Jem is very large, then the proper time according to Tom that corresponds to a certain amount of coordinate time is approximately going to equal the corresponding amount of proper time according to Jem multiplied by this square root factor, which is less than 1. Less time will pass according to Tom than it does according to Jim. Tom's clock is running slow according to Jim. That means that electromagnetic radiation will appear to be redshifted by this amount. For the interested, you can Google about gravitational redshift. You'll find that this effect is real and has been measured to high accuracy many times. The second variation on a theme that I'd like to look at is when the difference in radial coordinate for Jim and Tom is very small. I'll think of the radial coordinate for Jim as equaling that of Tom plus h, where h is small compared to our Tom. I can use techniques from calculus in order to get a reasonably nice formula for this redshift. In a situation where x is small, which it will be in the situation we're going to look at, 1 plus x raised to the k power is approximately 1 plus k times x. This is the beginning of the binomial theorem from Calculus 2. Taking advantage of that fact and writing delta tau Tom over delta tau Jim in terms of powers of things that look like 1 plus a small quantity, I'll be able to approximate this fraction in a reasonably simple way. Since in the current circumstances, I'm assuming that gm over one of these radial coordinates is very small, I will therefore neglect this term since it's the product of two terms that are very small compared to one. Doing some algebra, I find out that delta tau Tom over delta tau Jim is then going to approximately be this quantity. Using the assumption that h is very small compared to our Tom, I'll use the binomial theorem again. The ones inside the bracket cancel each other out. Before wrapping this up, it should be mentioned that this one is dimensionless. Gm over a distance squared has the units of acceleration. It has units of meters per second squared, while h would be in meters. So this factor, gm over r squared times h, has the same dimensions as a speed squared. So I can insert a c squared on the bottom of the fraction, which is 1 squared, and this will make the transition back to meter kilogram second units. In a near Newtonian situation, though, gm over radial coordinate squared is the Newtonian acceleration due to gravity. So proper time according to Tom over that of Jim differs from 1 by an amount that is the acceleration due to gravity over c squared times the vertical displacement between Tom and Jim. At first glance, it would seem to be impossible to measure such a thing in a ordinary laboratory type situation. If this is of interest, you might want to look up the Pound-Rebka experiment. This experiment has been repeated many times over the years with increasing accuracy. The results are in very good agreement with what general relativity predicts. The start of the new semester caused me a great number of delays. I believe, though, that I'm going to begin posting some videos on a semi-regular basis again. Until then, I hope everybody has a good day, and I'll see you again soon.